Frequency response can always help us analyze complex systems. Here we're going to show one example. For modulation and demodulation, we can use frequency analysis help us understand the system from inside out. So why do we have to do modulation and demodulation? For efficient transmission of signals, generally the size of the antenna need to be at order of the 10th of the wavelength of the signal. So if we try to broadcasting our voice message, our voice signal, then the acoustic signal is up to 20 kHz. Correspondingly, the antenna will be about 15 kilometers. That makes it impossible to transmit the acoustic signals directly at its original frequency. So the idea is, can we shift the acoustic signal to a different frequency? That frequency is high enough, will make the signal transmission more convenient. Another idea is, if we can shift the signal, original signal, to different location in the spectrum, then we probably can increase the efficiency of the transmission. So here is the image for radio. And we often see that there are two scales in the radio. We can change the setting of the frequency, and that frequency corresponding to the shifted signal's frequency. And we often see there's two symbols. One is AM, the other one is FM. So what do they represent? So we have to introduce the concept of modulation. We have a unit called modulator, help us implement the modulation. We want to transmit signal x of t. We call it modulating signal. The carrier will try to carry the modulating signal and transmit it to its destination. The carrier often defined by a cosine function. The cosine function has three different parameters: amplitude, frequency, and the phase. The modulating signal will try to change one of the three parameters so that the change of the parameters here will reflect the modulating signal. And the resulting signal is called modulated signal. Now let's try to do a comparison. Assume that we have a carrier described by this cosine function. If we use the modulating signal to modulate the carrier's amplitude, so the amplitude will change according to the modulating signal. We call this amplitude modulation. And in case we try to use the modulating signal to change the frequency of the carrier, then we're going to get a new signal like that. And this method is called frequency modulation. And in our course, we're going to focus on the amplitude modulation. The next is an animation, help us compare AM and FM. So in the modulated signal in AM, the amplitude is somehow changed according to the modulating signal, while in the FM, the modulated signal's frequency is changed according to the modulating signal. And here is the block diagram of the AM, amplitude modulation. Here we take one assumption that the amplitude and the phase of the carrier is equal to 1 and 0 respectively. This assumption is not necessary, but it will make our analysis simpler. So we're going to stick with this throughout this section. Now we use the cosine function as the carrier, and this is the modulating signal. If we try to do AM, the amplitude modulation, we can do simply multiplication in here to get the modulated signal. And assume this is the spectrum of the input signal. After multiplication by the carrier based on the modulation theory, we can get the spectrum of the modulated signal. And here is the graphic representation. So split it into two parts, one shift to your left, the other shift to your right. That is a graphic representation of the spectrum. So we get the modulation done. And this frequency can be really high, helping us transmit it easily. And this part is the other way around. We try to demodulate the modulated signal to get the original signal. So there's two parts. The first part is identical to the modulation part. And if we have the signal, modulated signal, what is the spectrum of x sub none? Since it's multiplied by the carrier, so we're going to repeat the modulation process one more time, split them by half, shift towards your left and right. And there will be an overlap at the DC and its surrounding area. So if we take a low-pass filter around here, then we can single this part out. And if we multiply the amplitude by 2, then we're going to get the original signal at the output end. So this is called the synchronous demodulation because we use the same carrier as we did in the modulation part. The frequency is the same and the phase is the same. Synchronous demodulation. Sometimes we think the regular demodulation is not very efficient because we know that for a real function, its spectrum got to be conjugate symmetric. So they are somehow redundant. So can we reduce the redundancy? Here is one option. We can use a technique called single sideband modulation to modulate the original signal. And here is how we do it. We do the regular modulation and then use a bandpass filter to take only the lower or the upper sideband so that can help us reduce the redundancy. And by selecting the passing band, we can selectively get the lower or the upper sideband. The problem, however, is we cannot implement it physically, the ideal bandpass filter. So we need to find another way. We have to use something called Hilbert transform to help us implement the single sideband modulation in the reality. It is more complicated. It has two branches. The upper branch, we use the regular modulation method. Well, the lower branch, we force the input going through Hilbert transform before it's modulated by a sine function whose frequency is the same as the carrier on the upper band, on the upper branch. And both modulated signal will sum up to get the final single sideband modulated signal. Now let's take a look at the Hilbert transform. And it's defined in the frequency domain as a sine function. And here is the frequency response in the frequency domain, and here is the corresponding impulse response of the same system in the time domain. Now let's try to analyze the system in the frequency domain. The upper band, if the input has a spectrum like that, and this part we already know is the split spectrum shifted towards left and right. So we'll put this aside. Now let's switch to the lower branch. The original signal going through the Hilbert transform first to get the spectrum like this. And when it's multiplied by a sine function, this spectrum will look like this. Considering both branches, the summation of these two modulated signals will reach a result like we expected, the lower sideband. And this is how we can use the Hilbert transform to implement the lower sideband modulation. With the concept of modulation and demodulation, we are able to analyze more complicated system. Here is one example. We have a quadrature amplitude modulation system. It has two channels as the input and correspondingly two channels as the output. And this part is the modulation part, and this is the demodulation part. Assume that the spectrum for this signal and the spectrum for this signal are given respectively. And we know that these two are ideal low-pass filters. The question is, could you determine the spectrum of the modulated signal? And here, the spectrum for this signal, A of t, and the spectrum of y sub 1 of t. The second part is the spectrum for B of t, the second branch, and the spectrum for y sub 2 of t. Now let's start from the first question. We have two branches, and the modulated signal is the sum of these two branches modulated signals. So the first branch we understand is based on the modulation theory, it will yield a spectrum like this, and the lower branch is multiplied by sine signal. So this spectrum is similar, but there's some slight difference. Negative sign and divided by 2 times the imaginary unit. And let's take a look at the real part of the modulated signal. It is the upper branch, and the imaginary part of the modulated signal is the lower branch. So they are in the real part and the imaginary part respectively of the modulated signal. So there's no interference between them. Let's take a look at the spectrum of the modulated signal, the graphic way. So we have the real part given in this expression. The real part is depicted in this plot. Well, for the imaginary part, it's related to the second signal. And here is the plot of the spectrum. Now let's switch to A of t at the demodulation end. This is in the upper branch. So the modulated signal is multiplied by the carrier. So here is the spectrum of A of t. Since this signal spectrum has the real part and the imaginary part, so let's separately consider these two parts. For the real parts, we move the expression in here. It related to the real part of the modulated signal in the frequency domain. What we can do is split this spectrum by half and then shift towards your left and your right. And at the DC components at the surrounding area, the spectrum will on top of each other. But for the imaginary part, we're going to do the same operation. At the DC components and its surrounding area, these two waveforms will cancel out each other. Therefore, after the ideal low-pass filter, the resulting signal is only related to the signals in the real part of the modulated signal, which is x1 of t. Well, now let's switch to the second branch, B of t. Because the modulated signal is multiplied by sine signal, this is the spectrum for B of t. Again, we need to separate the real part and the imaginary part and consider them separately. Due to the sine signal, the real part of B of t actually is related to the imaginary part of the modulated signal. So let's take a look at what's going to happen to this spectrum. What we need to do is, again, split it into half and shift towards your left and right. But part of it, you need to switch the sign. So here is the spectrum for the resulting signal. But for the real part, if we do the same operation, components at the DC area and the surrounding, the waveforms will be canceled out. So after the ideal low-pass filter, only the second signal spectrum will be retained. And clearly, it is identical to the second input signal. Next, we're going to introduce the concept of frequency division multiplexing. In general, radio frequency channel covers a large range, but for each radio station, they only need a very narrow band for broadcasting. Here is some data for medium wave band. It covers more than 1,000 kilohertz range, but for a radio station, the radio signal only needs dozens of kHz. So what we can do is we can divide the medium wave band into small bands, and each small band can be used by different radio stations so that we can broadcast multiple channels of radio station, radio signals. So here is the idea. If we use different carriers to modulate different radio signals, and then combine them together. And the modulated signal, if you look at that signal in the frequency domain, you will realize for different channels, they occupy different frequency bands. So there's no interference between them. And if we use bandpass filters with different frequency, we're going to separate different signals and then do the demodulation separately to get the signals in different channels without any distortion. And this is the idea of frequency division multiplexing. Thank you.